Hello friends, this is Hasiba. Welcome to today's session on perspective projection transformation matrix. In the last session, we have discussed about perspective projection coordinates, right? So under that perspective projection coordinates, we have seen two equations, right? So which are derived for xp and yp. So we'll be using the same perspective transformation equations as I'm showing here to you now, right? So xp is equal to x into zprp. Prp stands for projection reference point minus z viewpoint, right? So zprp minus zvp divided by zprp minus z plus xprp into zvp minus z divided by zprp minus z, and yp is equal to y into zprp minus zvp divided by zprp minus z plus yprp into zvp minus z divided by zprp minus z. These are the general perspective transformation equations, right? And we had also seen in the last session about the different cases, right? So four cases we had seen, and we had discussed about what do you mean by vanishing points and what are the three types of perspective projections, like 1-point perspective, 2-point perspective, and 3-point perspective, and a little bit insight on what do we mean by a frustum, right? So in today's class, we'll be discussing about the transformation matrix. So we use a three-dimensional homogeneous coordinate representation in order to express the perspective projection equations, right? So now only we just saw the perspective projection equations, right? So we'll be using homogeneous coordinates in order to represent the perspective projection equations in the form, right? So what we are doing here is I'm taking one variable, right, h, which is called as homogeneous parameter, and I'm assigning h is equal to zprp minus z, right? So in general, whatever equation we had written for xp, right? So in the above, that xp equation will be replaced just by xp is equal to xh by h, right? So where xh is nothing but the homogeneous parameter on x-axis, which is equal to x into zprp minus zvp plus xprp into zvp minus z, right? So the denominator value, which was zprp minus z, is replaced by h, right? So you can see here our parametric equation. So what we are doing for our parametric equation is zprp minus z, I'm making it as h, right? So if I take this value as h, right, so I'll get only the topmost part, xp will be x into zprp minus zvp plus xprp into zvp minus z divided by whole divided by h, because the denominator is common here, which is zprp minus z, right? So in the above equation, just I'm replacing h by zprp minus z, then I will get xh. The same way I will get yh is equal to y into zprp minus zvp plus yprp into zvp minus z, right? So the perspective projection transformation of a v in coordinate position is done by two steps. That means if I have to have a perspective projection transformation matrix, right, so then we have to follow the two steps. What are the two steps? First, we have to calculate the homogeneous coordinates, right? So first and foremost, we have to calculate the homogeneous coordinates using the perspective transformation matrix, right? So to find the homogeneous coordinates, right, so ph stands for perspective homogeneous coordinate matrix, right? So this is a column matrix which is equal to m is the transformation matrix for perspective projection. So m pers in dot p, right? So p is the matrix for the coordinate representation. So ph will be the column matrix representation. We will write it as xh, yh, zh, comma h, right? So because this is the perspective transformation homogeneous coordinate matrix, that is why it is xh, yh, zh, comma h. And what is p? P is our regular column matrix, right? So what we use for normal points, right, as x comma y comma z comma 1, right? So the first step is we have to calculate the homogeneous coordinates using the perspective transformation matrix, right? So once we get the homogeneous coordinates for this transformation matrix, what we have to do is second we have to apply the normalization transformation and the clipping routines, so that the homogeneous coordinates are divided by the parameter h in order to obtain the true transformation coordinate position, right? So once we get the transformation matrix, right, so the second step what we are doing, we are going for normalization transformation, right? So we will normalize and we will clip, right, and then what we do, we divide this homogeneous coordinates will be divided by the parameter h, because that is the original parameter what we are taking. So if I divide everything by h, then I will get my true transformation coordinates. Yes or no? Xh by h means I will get my x dash, right, or xp. Yh by h means I will get my yp. Zh by h means I will get it as a zp, and h by h means I will get 1. So this, yeah, all the values will be xp, yp, zp, comma 1. That means this is a point on my view plane, right? So that is nothing but the two transformation coordinate positions, right? So in order to do that, right, so the my perspective projection matrix M pers is given by, this is my perspective projection matrix, right? So under x we have zprp minus zvp, right? So on y also it is zprp minus zvp, right? So minus xprp minus yprp sz. Here we have xprp, zprp, yprp, zprp, right? Tz, zprp, and minus 1, right? So this is our perspective projection matrix, right? So we wrote this matrix by using this equation only, right? So x into zprp minus x into zvp, right? So using that only we have written this perspective projection matrix, right? So here the parameter sz and tz are nothing but our scaling and the translation parameters for normalizing the projected value of the z coordinate. In order to normalize the projection values for the z coordinate, what we are doing, we are using two factors, which are scaling factor and translation factors along z-axis, right? So the values depend on the normalization range what we select, right? So normalization varies from -1 to +1. So the next topic is symmetric perspective projection frustum, right? So far we have seen a frustum, right? So frustum is a truncated pyramid, right? It is also called as the view volume on the view plane, right? So yeah, I can have my frustum as a symmetric also, right? So what do we mean by symmetric perspective projection frustum, right? So if at all I take, say for example, a line is drawn from the center of a projection on the view volume, right? So if the line from the projection or reference point, that is my center of projection, through the center of the clipping window, right, and on through the view volume, right? If at all I draw a line from the center of a projection, right, so through the clipping window, this is my clipping window. If I draw a line from the center of projection to the clipping window, right, so which crosses through the view volume, right, and it is the center line of the perspective projection frustum. If at all it is the center line of the perspective projection frustum, then what happens, this center line, we say it is perpendicular to the view plane, right? So this center line, whatever we have drawn, it is perpendicular to our view plane, right? So thereby it creates a symmetric, right? So my frustum is symmetrical to my view plane, right? So because the frustum center line, it intersects the view plane at the coordinate location, which is xprp, yprp, and zvp, right? So xprp is x projection reference point, y projection reference point, and zv plane, right? So this since it is perpendicular, what happens is it creates the frustum becomes symmetrical to that of the view plane, right? So that is why it is called as symmetric perspective projection, right? So my frustum view volume, whatever is there, that is symmetrical to my view plane, right? So you can see this point is called as the projection reference point, which is xprp, yprp, zprp. What we are doing, we are drawing one line from this particular point to the view volume, right, such that that line is perpendicular to the view plane, right? So since it is perpendicular to the view plane, what happens, it makes my view volume appear to be symmetrical to the view plane, right? So the point which is projected on the view plane, as we had earlier, it is xprp, yprp, and zvp, right? So if for the frustum view volume, we have two types of planes, near plane and far plane, right? So the one which is closer to my view plane, I call it as the near clipping plane, and the one which is far, I call it as the far clipping plane. And the line which is drawn, right, so that particular line I call it as the frustum central line, right? So because the frustum central line, it intersects the view plane at the location xprp, yprp, and zvp, we can express the corner position of the clipping window, right? So this is my xw min, yw min, right, and this is my xw max, yw max, right? So we can represent the corner position in terms of the window dimension, right? So look at the formula. The formula for xw min will be given by, right, so since the center is xprp, so xprp minus width by 2. As we can see, the width and height of the clipping window is reduced to half of its size, right? So that is why xw min will be xprp minus width by 2, and xw max will be xprp plus width by 2, right? So xw min, xw max. Next I have yw min and yw max, right? So yw min will be yprp minus height by 2, and yw max will be yprp plus height by 2. right? So once we specify the corner position of the clipping window, right? So another way to specify symmetric perspective projection is to use the parameters that approximate the property of a camera lens. That means whenever I click a photograph, right? So a photograph which is clicked, it is produced with a symmetric perspective projection of a scene onto the film plane, right? So whenever I'm clicking any picture, say for example, I'm using my mobile phone, right? And I want to click a picture of this, what happens? The line is the this is my center of projection, right? So the line is perpendicular to the view plane, right? So the line which from the center of projection, it is perpendicular to the view plane. So whenever it is perpendicular to the view plane, right, I say that it has created a symmetric frustum, right? So the reflected light rays from the objects in a scene are collected on the film plane from within the cone vision of the camera. So this cone vision can be referenced with a field of view angle, right? So we have we can view it from an angle which is a measure of the size of the camera lens. Large field of view angle, for example, corresponds to a wide angle lens, right? So if at all I have a large angle, the angle is big, means that means I have a my lens is big, right? So in computer graphics, the cone of vision, it is approximated with a symmetric frustum, and we can use a field of view angle to specify an angular size of for the frustum, right? So you can see here we have specified the angle. This angle theta is called as the field of view angle, right? So here I have my clipping window. This is my frustum view volume, right? So whenever it is directly perpendicular, right, so then my frustum will become symmetrical, right? So at that time, right, so I have an angle. This particular angle we call it as the field of view angle. So for a given projection reference point and a view plane position, the field of view angle, it determines the height of the clipping window, right? So from the right angle triangle, right, so we can calculate the height of this particular clipping window. I have a right angle triangle here, right? So I will take this right angle to triangle and I can divide the entire angle theta, right? So consider this part, right? So this is the part what we are considering. This forms a right angle triangle. This height of the clipping window, right? So along with this dotted line and this dotted line, right? So height of the clipping window, dotted two lines. This is my projection reference point. The entire angle theta, right? So if I take the symmetrical frustum volume, that means what? The center of a projection, it is perpendicular to my clipping window, right? So I will draw a line from my clipping window to the center of projection, right? So what happens at that time? The entire angle theta, which is here, it is divided into two halves. So I will get it as theta by 2, theta by 2, right? So now let this point is what? This point is xprp, yprp, and yprp and zprp. This is the point, but on the view plane it is xprp, yprp, and zvp, right? So the distance here, it will be equal to zprp minus zvp, right? So the distance between the center of projection and the point on the clipping window will be zprp minus zvp. And what is this? This is my height of my clipping window. So we are considering this part of the right angle triangle, right? So this is my focus of this part, is what I am focusing, right? So this is my right angle triangle, what I am focusing, right? So I will get like this. So this point is for projection reference point, and this point is a point on the clipping window, right? So we know that projection reference point is what? It is xprp, yprp, and zprp, whereas on the view plane it is xprp, yprp, zvp, right? So that is why I will consider the distance here as, since this is zprp and this is zvp, the distance between these two will be zprp minus zvp, right? So now if I take the tan of the angle, what is tan? Tan is nothing but your adjacent by hypotenuse, right? So we have cos theta, sin theta, and tan theta. So I'm taking the tan of the theta here, tan theta here, right? So I will get it as opposite by adjacent, right? So what is the opposite side? Opposite side for this particular angle is this is the opposite side. This is opposite by adjacent, sorry, it is opposite by adjacent. So I will take this as opposite. What is the opposite? This full is the height, so this will be height by 2. So height by 2 divided by adjacent. What is the adjacent here? zprp minus zvp. This is the adjacent side. So tan theta by 2 will be equal to height by 2 divided by zprp minus zvp, right? So that the clipping window, height of the clipping window will be equal to, if I multiply these two, what I will get? I will get 2 times of height will be equal to 2 times of zprp minus zvp into tan of theta by 2, right? So therefore the diagonal elements with the value zprp minus zvp could be either of the following two expression, right? So that means I can take the, if I have to find zprp minus zvp from this formula, right? So what I will do, I will take zprp minus zvp will be equal to height divided by 2 into tan inverse of theta by 2. So tan inverse theta, we know that inverse of tan theta is cot theta. So I will get it as ZPRP minus, just I'm calculating using this formula, I'm calculating ZPRP minus ZVP. So ZPRP minus ZVP will be equal to height by 2 into tan inverse of theta by 2. Tan inverse of theta by 2 is nothing but cot of theta by 2. Right, so that is why I will write ZPRP minus ZVP will be equal to height by 2 into cot of theta by 2. Right, so the same way I can get what is height by 2. Height by 2 is nothing but I can write it as which is also equal to width into cot theta by 2 divided by 2 into aspect. Right, so aspect ratio. Right, so we have already studied in the first module, so we'll just write this distance. Right, so ZPRP minus ZVP. Right, so which is nothing but our aspect. Right, so next, the next topic is oblique perspective projection frustum. Right, so we have seen symmetric perspective projection. So what is symmetric perspective projection? So if at all I draw a line from the center of a projection to the view volume, right, and if that particular line is perpendicular to the view plane, then whatever frustum I get is symmetric perspective projection. Right, so the same way I'll have oblique perspective projection frustum. Right, so in oblique perspective projection frustum, the center line of perspective projection view volume, it is not perpendicular to the view plane. Right, so if at all I draw a line from the center of projection, right, to the view volume, then it is not perpendicular. If it is perpendicular, it becomes symmetric. If it is not perpendicular, then I call it as an oblique projection. Right, oblique perspective projection frustum. Right, so you can see here I have the center of projection, which is XPRP, YPRP and ZPRP, and I am drawing a line from this particular point here. All right, so to the view volume, and this is not perpendicular to the view volume. Right, so since it is not perpendicular, so I call it as oblique perspective projection. So this is the clipping window, this is my view plane. Right, so this is my near clipping plane, far clipping plane, and this is my frustum central line. So in this case, we can first transform the view volume to a symmetric frustum and then to a normalized view volume. Right, so an oblique perspective projection view volume can be converted first to a symmetric frustum by applying a z-axis shearing. Right, so we have to shear this with respect to transformation matrix. Right, so you have already studied reflection and shearing. Right, so we have discussed different types of transformations like translation, rotation, scaling, right, reflection and shearing. Shearing is to either to keep one axis constant and reduces on the other, x shear, y shear. Right, so everything we have done. That means I can convert my square to a parallelogram. Right, so we have seen that example for x shear, y shear. The same way I can have, in order to convert my oblique perspective projection to symmetric perspective projection, what I am doing here is I am applying z-axis shearing transformation matrix. Right, so this transformation, it shifts all the position on any plane that is perpendicular to the z-axis by an amount that is proportional to the distance of the plane from a specified z-axis reference position. Right, so when you perform this z-axis shearing, what it will do, it will transform, it will shift all the positions on any plane which is perpendicular to the z-axis. It will shift the values of all the points which are perpendicular to the z-axis by an amount which is proportional to the distance of the plane from the specified z-axis reference position. Right, so what is the amount? It will shift by an amount which is proportional to the distance of the plane. Right, so distance of the plane from the specified z-axis reference position. Right, so in order to do this computation, we have the matrix here. The computation for shearing transformation as well as for perspective and normalized transformations are greatly reduced if we take the projection reference point to be the viewing coordinate origin. Right, so in order to do all these shearing and all, we take our projection reference point will be as the origin. Right, so take the projection reference point XPRP, YPRP, ZPRP as 0, 0, 0. Right, so we will obtain our shearing matrix. Matrix for Z shear is 10 SHZX 0, 01 SHZY 0, 00 10 000 Right, for any three-dimensional transformations, we will have a 4x4 matrix. Right, so you have to remember that, because one for x, y, z, and then homogeneous representation. Right, so we need to choose values for the shearing parameter in such a way that, right, so we have we should take the values as 0, 0, z near 1. Right, so which which is equal to mz shear. We have to multiply it with xw min plus xw max by 2 and yw min plus yw max by 2, z near and 1. Right, so now if I multiply these two matrix, right, then I will get the formula for SHZX right? So SHZX will be equal to minus XW min plus XW max by 2, right? So this value is my minus XW min plus XW max divided by 2 into Z near, right? So just multiply these two matrices, right, and equate it to 0, 0, Z near 1. You will get the solve for SHZX. You will get this value SHZX and SHZY, right? So similarly with the projection reference point, right? So at the viewing coordinate origin and with the near clipping plane as the view plane, the perspective projection matrix, right? So whichever perspective projection matrix we had here, right? So M perspective projection matrix we had written in the above equation, right? So perspective projection matrix. So this M perspective projection matrix, if I take XPRP as 0, YPRP as 0, ZPRP as 0, right? So what will happen? So it will be reduced to one more matrix, right? So that is what we are getting here by replacing XPRP, YPRP, ZPRP as 0, right? So all these will get cancelled and your ZVP, we are taking it as a near clipping plane, right? So as you can see here, if I go back, my ZVP, I'm taking it as my near clipping plane, right? So here it is 0. 0 minus ZVP, I will get ZVP is my near clipping plane. So Z near. Here also I will get it as Z near. This is 0, this is 0, SZ will be there, minus 1. This is 0, this is 0, TZ will be there, and this is also 0, right? So like that, we will just substitute XPRP, YPRP, ZPRP value, and I'm taking my view plane as my near view plane, right? So same thing we have got here, right? So now what we have to do, we have to multiply the perspective projection matrix into my shear matrix, right? So that I will get my oblique perspective matrix, right? So how I'm getting the oblique perspection? By multiplying the perspective projection matrix with the shearing on Z axis, right? So I will multiply my perspective projection matrix with the shearing matrix on Z axis. If I multiply these two, I'll be getting this matrix. So this matrix is my oblique perspective projection matrix, right? So like this, you have to perform oblique perspective projection transformation, right? So the next topic is normalized perspective projection transformation coordinates. That means how to normalize the coordinates for perspective projection transformation. So when we divide the homogeneous coordinate by the homogeneous parameter h, we obtain the actual coordinates which are orthogonal projection coordinates, right? As we have seen that we will be writing xh, yh, zh, comma h, right? So if I divide all those by h, right, then I'll be getting my xp, yp, zp, comma 1, right? So that is my original actual projection coordinates. So the final step in the perspective transformation process is to map this parallel pipe, right? So we have to map this parallel pipe which I have got the view of the parallel pipe, the view volume, into a normalized view volume, right? So we have to map this projection perspective projection view volume to a normalized view volume. So the transformed frustum view volume, right? So which is mapped which is rectangular parallel pipe. This is the transformed frustum view volume which is rectangular parallel pipe. We have to map it to a symmetric normalized cube within a left-handed coordinate reference, right? So left-handed coordinate reference, x normal, y normal, z normal. We have to normalize with respect to the unit cube, which is -1, -1, -1 to +1, +1, +1, right? So this is my frustum view volume what I have got. So I am applying the normalization, right? So that I will get it as a normalized view volume, which is my unit cube, right? So because the center line of the rectangular parallel pipe view volume is now the Z view axis, right? So as you can see here, the center line of my rectangular parallel pipe view volume is my Z view axis, right? So no translation is needed in the x and y normalization transformation, right? So we just require only the x and y scaling parameters which are related to the origin. Since it is in the line of Z view axis, we will not apply any of the x and y scaling parameters, right? So just we will require only x and y scaling parameters. We need not go for any translation, right? So just we have to scale it along x and y so that my rectangular becomes cube, right? So I'm reducing the size here. I'm reducing the size of my rectangular to become cube. That is why I'm going for scaling, right? So as we know, scaling is for making it bigger or smaller, right? Translation is to shift the place, right? So I'm not doing any translation here, right? So I'm just scaling the values of x and y so that my rectangular will become a unit square cube, right? So that is why I'll go for scaling matrix. So I will go for xy scaling. So sx0 0 0 sy 0 0 0 0 1 0 0 0 1, right? So now I have to multiply this xy scaling matrix with our oblique perspective projection matrix, right? So if I multiply this scaling matrix with my oblique perspective projection matrix, then I will get my normalized perspective projection matrix, right? So just multiply this and this, you will be getting your resultant normalized perspective projection matrix, right? So from this transformation, right, so once we obtain the normalized perspective projection transformation, so if I multiply it with xyz comma 1, I'll be getting my actual homogeneous coordinates, right? So which we wrote xp as what, xh by h, right? So just multiply m normalization into xyz1, right? So if you multiply, you will be getting these values, right? So yp is equal to yh by h, you will be getting these values. Zp is equal to z by h, you will be getting these values, right? So to normalize this projective transformation, we want the projection coordinates of xp, yp, zp should be from -1, -1, -1 to +1, +1, +1. That is my normalized unit cube, right? So that is why xp, yp, zp will be from -1 to +1 range, right? So input a, so this is nothing but your xw min, yw min, and for z, for z we will not write it as z min, z max, we will write it as z near and z far, right? So xw min, yw min, z near, because it is from near clipping plane to far clipping plane, z far, right? So and I will obtain what is sx, sy, sz, right? So I have tz and all the elements of the normalized transformation matrix for general perspective projection, right? So just replace sx, sy, sz and tz in this normalized perspective projection matrix, right? So you will be getting your final matrix as this, right? So this is your normalized perspective projection transformation, right? So whatever perspective projection you have done, you are making it to become a normalized cube, right? So that is perspective projection transformation. So the last is the viewport transformation at the 3D screen, right? So whatever we have normalized, now I have to convert it into my viewport coordinates or my 3D screen coordinates. So once we have completed the transformation to normalized projection, once we have completed the transformation to normalized projection coordinates, now clipping can be applied efficiently to the symmetric cube, and then the contents of the normalized view volume can be transformed to the screen coordinates, right? So after you normalize, what is the last step? You have to display that particular object onto your screen, right? So in order to display onto the screen, right, so position throughout the three-dimensional view volume, they also have the depth coordinate. That means for a 3D picture, we also have a z coordinate, and we have to retain this depth information for visibility testing and surface rendering algorithms, right? So we have to include this z renormalization. So the transformation for the normalized view volume to the 3D screen, right, so is given by this transformation matrix. So you have to remember this. We are just converting our normalized matrix, normalized perspective projection matrix to a 3D screen coordinate. So we are converting it into a viewport coordinates, right? So in normalized coordinates, z normal was -1. Face of the symmetric cube, it corresponds to the clipping window area, and this face is mapped to the rectangular viewport, right? So which is now referenced at z screen as 0. That means I'm converting my normalized screen, right? So normalized coordinates to my screen coordinates. So I'm taking my z screen as 0, right? So the viewport screen area will have xv min, yv min and 0, and xv max, yv max and 0, right? So because my viewport is what? My viewport is a 2-dimension, right? So till now we had 3-dimension normalized projection, that we have to convert it into a screen coordinate, right? So in my screen coordinate, it is only 2 dimensions, so I will have only x viewport min, y viewport min comma 0, right? Z axis will be 0 here, and right corner will be x v max, y v max comma 0, right? So this is how I can convert the transformation whatever we have done to the viewport, right? So viewport is nothing but screen coordinates. So the next topic is OpenGL 3-dimensional viewing functions, right? There are so many OpenGL viewing transformation functions. The first function is GL matrix mode, GL underscore model view, right? So this is a matrix which is formed and it is concatenated with the current model view matrix, right? So we have seen that GL underscore model view, what it will do, right? So since any transformation in graphics is matrix multiplication, so we have to consider this model view matrix. What it will do, it will multiply the current matrix, it will multiply the current model view matrix. It is basically used for multiplication, right, or transformation or composite transformation. So initially what we do, will have a GL load identity matrix. So that load identity will be multiplied with the current matrix, right, and the current will be multiplied with the further matrix, like that, right? So in order to have composite transformation, we'll be using GL underscore model view. Then we have used one function which is called as GLU lookat, right? So this function we had used in 4th lab program where we had done perspective projection, right? So GLU lookat, we have, it has how many parameters? It has 9 parameters: x naught, y naught, z naught. That is my origin. X reference, y reference, z reference. That is the point on my view plane. Vx, vy, vz. It is the point on my it is the view up vector, right? So viewing parameters are specified with the above GLU function, that is graphics library function. So this function designates the origin as the viewing reference frame, right? So that means I'm taking my origin as my view plane point, right? So coordinate position P naught as my point on the view plane is x naught, y naught, comma z naught. The reference position here is x reference, y reference, and z reference. This is my reference projection point, right? And the view up vector, right? So is vx, vy, vz. So by default we say I'm looking from z axis and I'm viewing along y axis, right? So if you take this laptop as an example, right? So when I'm viewing this laptop, right? So I'm viewing along y axis, right? So you can see that my view up vector, this entire laptop screen, I am viewing along y axis, view up vector, and from which angle of which axis I'm seeing. If this horizontal is my x axis, this horizontal is my x axis, and this height is my y axis, then I am seeing from the front view, right? So that front view, we call it as the z axis, right? So that is why we write P naught, which is my point at the origin. It is 0, 0, 0, right? So my reference point, that means my center of projection or my projection from where I am seeing. This is my viewer's view, right? So the camera position. So the camera position or the viewer's point is from z axis, right? So z axis is always from this side I'm seeing, right? So that is why I'm taking the negative z axis, 0, 0, -1, right? So and what is my view up vector? Up vector is I'm seeing along the y dimension, so it is 0, 1, 0, right? So the same values we have taken for our 4th lab program, right? For the rotation of a cube, right? So where we can do plus x2 in order to maximize the cube, right? So if I do negative, then the cube will shrink and it will fade away, right? So the next is OpenGL orthogonal projection function, right? So GL matrix mode, GL underscore projection, you know this, it is basically used to set up a projection transformation matrix, right? So we can issue any transformation command and the resulting matrix will be concatenated with the current projection matrix. GL ortho function, you know what is ortho, right? So it has 6 parameters: xw min, xw max, yw min, yw max, and d near and d far. That is d near and d far, they denote the distances in the negative z view direction, right? That means near and far view, that is the z axis, right? So we can assign the values like this, you know, right? So -1, 1, -1, 1, -1, 1, right? So any values you can assign for GL ortho, right? So the last 2 functions what we are seeing here for perspective projection function is GL frustum. So GL frustum takes 6 parameters: xw min, xw max, yw min, yw max, and near and far, right? So as we have seen here in the diagram, any frustum will have what? It will have it is the same like the clipping window, right? So that a clipping window, right? So it will be extended and I will get a view volume, right? So which is a truncated pyramid, right? So like this I will get, right? So this is my view volume, right? That means whatever object is there within this particular volume I can see, right? So if I take my frustum, the frustum also has xw min, yw min. This is my xw max, yw max, and it will have the near clipping plane, and this is the far clipping plane, that is z near and z far, right? So totally 6 arguments it takes, right? So GL frustum will take 6 arguments, right? So what is frustum? It is a truncated pyramid for view volume, right? So that means whatever is there within that particular view volume we can see. So it specifies a perspective projection that has either I can have a symmetric frustum view volume or I can have oblique frustum view volume, right? So and all the parameters are, so I can have double precision of floating point numbers, right? So these are the xw min, xw max, they set the coordinates for the flipping window on the near plane. YW min, YW max are setting the coordinates for the clipping window on the far plane, right? So near is nothing but positive z axis, far plane is nothing but the negative z axis, right? So the last function is our GL viewport function, right? So GL viewport, it has 4 things: xv min, yv min, and YP width, VP width, and VP height, right? So that means xv min is viewport viewport x-axis minimum, viewport y-axis minimum. This is viewport width and viewport height, right? So rectangular viewport will be defined. So this viewport is nothing but what you will be seeing on your screen coordinates, right? So we have a viewport. The first two parameter in this function, they specify the integer screen coordinates of the lower left corner of the viewport, which are relative to the lower corner of the display window. If I take my laptop as my viewport, right? So this part is my X vmin and Y vmin, right? So whereas this part is my VP width and VP height, viewport width and viewport height. So to maintain, we set the aspect ratio of the viewport, which is equal to the aspect ratio of the clipping window, right? So the display windows are created and managed by using the glut routines. The default viewport in OpenGL is the size and position of the current display window, right? So if at all you have not given the viewport, then whatever is the size of your display window, the same thing will be your viewport, right? So we have also seen how to make use of the viewport in your Cohen-Sutherland line clipping algorithm also, right? So we have seen what is the difference between window and viewport, right? So this completes the first part of your fourth module, which is 3D viewing and 3D projections. Thank you.